So we are going to get an expression for, we are going to obtain an expression for magnetic field, going to obtain an expression for magnetic field at a point along the equatorial line, along the equatorial line of a magnetic dipole, or instead of magnetic dipole, you can say it out as a Bohr magnet. So in our last class, we have studied about the expression for the magnetic field at a point along the axial line of the magnetic dipole, and here we are going to determine the magnetic field at a point along the equatorial line of the magnetic dipole or the Bohr magnet. So in order to study this, first of all, let us consider a Bohr magnet. So if I am taking a Bohr magnet or a magnetic dipole, let us represent it as the south pole at one end and the north pole at the other end. As we know, the axial line is the line which joins both the poles. The length of this magnet or Bohr magnet or this magnetic dipole is considered to be equal to 2L. Let O be the geometric center. If so, this length OS is equal to L semi-length and ON is also equal to L semi-length. So I can say what is the magnetic dipole moment of the magnet. So the magnetic dipole moment of this Bohr magnet is one of the pole strength. So we have to take the pole strength on both ends as QM. So magnetic dipole moment is the product of the pole strength QM and the shortest or the perpendicular distance between the two pole strengths. So the dipole moment PM is equal to 2 into QM into L. Now, what we have to consider? We have to consider a point on the equatorial line. So I am considering an equatorial line by dropping an perpendicular to the axial line. If I am dropping a line perpendicular to axial line, that line is considered as the equatorial line. On that equatorial line, you consider or you take a point P, or according to your book, it is C. Let the point C is at a distance of small r from O. Now, the point C is experiencing two magnetic fields, one due to north pole and another due to south pole. So if I am considering the magnetic field at C due to north pole, then it is acting along the line joining the north pole and the point C, and it is acting away from what? Acting away from that of C. So let us consider that magnetic field as Bn. Let us write this Bn vector. This distance Cn, I am taking it as R dash, which is equal to, using the Pythagoras theorem, I can consider R dash square is equal to R square plus L square. So R is equal to root of R square plus L square. Similarly, the point C will be experiencing a magnetic field due to the south pole, which is acting along the line joining the south pole and the point C, but acting towards that of the south pole. Because the force will be along the direction of the force, the magnetic field will also acting. That force I am considering, that magnetic field I am considering it as Bs vector. So based on this, since the C is experiencing two magnetic fields at this point C, I have to calculate the resultant magnetic field B at C, which will be acting parallel to that of the axis opposite to dipole moment. Let us calculate how. So the resultant magnetic field B vector has to be calculated. That is the resultant magnetic field at C. So let us consider this angle as theta and this angle of inclination as also as theta. What is the value of this CS? That also equal to R dash, which is equal to root of R square plus L square. So for drawing this diagram, I have given some description. Let us write that description as a small part. So first of all, you have to write like this. Consider a bar magnet. Consider a bar magnet NS of length 2L, having a pole strength QM on each end, on each pole, on each end, having a pole strength of QM on each end. See what I have to calculate. To calculate magnetic field, at C. First of all, you have to place a unit pole strength. Unit pole strength means you have to place 1 ampere meter of QM. So unit pole strength at C. Now at C, the net magnetic field can be calculated. The net magnetic field B vector can be calculated using the superposition principle. That is, B vector is equal to the vector sum of the magnetic field developed at C due to the North Pole and the magnetic field developed at C due to the South Pole. So this B vector we have to calculate. For that, first of all, I am calculating what is the magnetic field at C on which we are on C due to North Pole and due to South Pole. So in order to calculate, here 1 ampere meter of pole strength is placed. Okay, let us move on to the theory. First of all, I am calculating the magnetic field. I am calculating the magnetic field at C due to North Pole. The magnetic field at C due to North Pole. What is this? So the magnetic field at C due to North Pole is Bn. What is Bn vector? In the last class itself, I have told you. Force acting on this unit charge or unit pole strength divided by the pole strength placed at that point. So I can write B vector is equal to, Bn vector is equal to, what is force? Mu0 divided by 4 pi into. What is the value? Qm. Here you are having pole strength Qm. Here you are having the pole strength as 1. So Qm into 1 divided by square of this distance, that is R dash square, isn't it? R dash square by Qm. Qm placed at C is 1. So by 1 is the same formula. So Bn vector equal to mu0 by 4 pi into Qm by R dash square. Any difficulty? Okay. Now this Bn is taken to be mu0 by 4 pi into Qm divided by R dash square. Let us consider or take this as equation number 1. Now we have to resolve this into two components. You resolve this Bn into two perpendicular components. So if you are resolving it into two perpendicular components, what are the two components? I am drawing a diagram here. See, this Bn is acting along this direction. Isn't it? One is acting along this direction and another one is acting in this direction. So I can draw a diagram. This Bn vector is acting along this direction. If I have to resolve it into two components, means I have to take the axis as the reference. So along this direction, the axis is available. Here you are getting the angle theta. So one is the horizontal component. If you are considering them, one will be the horizontal component and another resolution is along the vertical component. You see, the horizontal component is, horizontal component is to the adjacent side. So horizontal component is Bn cos theta. Vertical component is opposite to theta. So I can write it as Bn sin theta. So resolve Bn into two perpendicular components. One on the horizontal component. The horizontal component from the diagram, I am writing it as Bn cos theta. And another one is the vertical component. Both are perpendicular to each other. The vertical component is nothing but Bn into sin theta. You see, Bn cos theta is acting along the x-axis in the negative direction. So here I am writing minus I cap. Bn sin theta is acting along the y-axis in the positive direction. So Bn sin theta, I can write it out as j cap. Hope you should have understood. Similarly, I am calculating magnetic field at C due to South Pole. So here I am writing. So I am writing here again magnetic field at C. Magnetic field at C due to what? Due to the South Pole. So magnetic field at C due to South Pole abdina BS vector which is equal to adhe madri force F vector divided by pole strength. Look at the diagram and write BS vector is equal to the same magnitude mu0 divided by 4 pi into QM divided by R dash square. Take this as equation number 2. Now what you can do to resolve this? Again you write resolve this BS. Resolve BS vector into two perpendicular components. Okay, look at the diagram. In what direction that force, that magnetic field is acting? See, from C to B. Then I have to write along this direction. This point is C. So at this position, you are having S. Here you are having N. Along this direction, we are getting BS vector. So this angle is also considered to be theta. Now you resolve this BS. When you are resolving this BS, one is along the horizontal direction and another one is along the vertical direction. Horizontal is adjacent side. So you get BS cos theta. Then vertical is vertical component is opposite. So we can write BS sin theta. Now again I can write when BS is resolved, see the horizontal component is equal to BS cos theta. Along what direction? It is also acting along the x-axis in the negative direction. So minus I cap. What is the vertical component? When I am considering the vertical component, it is BS sin theta, which is acting along the y-axis in the downward direction. So it is minus j cap. Am I correct? Am I correct? Now you compare these two. See, when you are considering the resolved components, here I am writing. The vertical components are equal in magnitude and opposite in direction. So they cancel each other. So vertical component won't contribute to resultant magnetic field. But on a horizontal components are acting along the same direction. So the resultant magnetic field is sum of the horizontal components. So vertical components are cancelling each other. But enna padikirom? But the horizontal components are, but from the diagram, it is clear that the horizontal components are acting along the same direction, same line and same direction, along the same line and same direction. So direction. So net magnetic field is equal to net magnetic field at C is equal to sum of the horizontal components. Sum of the horizontal components. So how I can write then? Total magnetic field at C B vector is equal to the horizontal component of Bn. Bn cos theta minus of I cap plus Bs cos theta along the horizontal direction minus of I cap. Hope you should have understood this. See here we can write Bn is equal to Bs. Magnitude of Bn vector, magnitude of Bs vector equal. What is its value? Mu 0 divided by 4 pi into Qm by R dash square. See, what is this R dash? R dash is equal to root of R square plus L square. Therefore, magnitude of Bn vector is equal to magnitude of Bs vector is equal to mu 0 divided by 4 pi into Qm by R dash square பண்ணீங்கன்னா you can get R square plus L square. So take this and substitute it here to get what? To get the resultant. What is the resultant then? We can write that resultant as, how I can write? B vector is equal to, isn't it? B vector is equal to, I can write this Bn vector plus Bs vector. So இங்க horizontal component மட்டும் ஆட் பண்ணணும். புக்ல உள்ள கான்செப்ட் படி நான் வர்றேன். எப்படின்றது சொல்லிடலாம். ஒண்ணும் இல்ல. What is this Bn vector? Bn vector is the horizontal component plus vertical component. What is that horizontal component? Horizontal component is minus of Bn into cos theta of I cap. Then what about the y component? The y component is considered to be cancelling each other. அதனால அதை விட்டுருவோம். அடுத்து plus திருப்பி Bs vector உடைய horizontal component minus of Bs into cos theta into I cap. Am I correct? So the horizontal component of Bn vector and horizontal component of Bs vector. அதான் இங்கே எழுதி இருக்கிறேன். அதான் நான் திருப்பியும் எழுதுறேன். So B vector is equal to, இதுல Bn-க்கும் Bs-க்கும் நம்ம சப்ஸ்டிடியூட் பண்ணணும். ரெண்டுமே சேம்னு சொல்லிட்டோம். நான் திருப்பி எழுதியிருக்கேன், தேவையில்லை, திருப்பி எழுதியிருக்கிறேன். ஸோ ரெண்டுமே சேம்னு நம்ம சொன்னதுனால நம்ம என்ன பண்ணலாம்? மைனஸ் ஆஃப், இல்லைன்னா கூட ஒரு ஸ்டெப் எழுதுவோமா? மைனஸ் ஆஃப் Bn இன்ட்டு காஸ் தீட்டா ஐ கேப் பிளஸ் இன்ட்டு மைனஸ் ஆஃப் Bs இன்ட்டு காஸ் தீட்டா ஐ கேப். இப்போ சிம்பிளிஃபை பண்ணுவோம். How to simplify? See, I can write B vector is equal to minus of இங்க ஒரு Bn, இங்க ஒரு Bn. I can write it out as both are same. அப்ப நான் இப்ப எப்படி எழுதிக்கலாம்டா இத? minus of Bn cos theta I minus of Bs cos theta I. Since Bn is equal to Bs அப்படின்னா இந்த Bs க்கு பதிலா Bn போட்டு எழுதுனா minus of 2Bn or Bs cos theta I cap. Am I correct? See, instead of this Bs, if I am putting Bn, minus a common எடுத்துட்டேன்னா Bn cos theta I plus Bn cos theta I. So I am writing B vector is equal to minus of 2 into Bn into cos theta into I. Now you substitute for Bn or Bs magnitude or value. We get B vector equal to minus of 2 into Bn. What is the value? Mu 0 divided by 4 pi into Qm divided by R square plus L square. Then multiplied it with cos theta into I cap. Am I correct? Now you consider the triangle. So let us take this as equation number 3. Now you from figure you consider a right angle triangle. In the right angle triangle, you just take the figure. See, let us consider this triangle OSC. RONC. So from triangle NOC or S triangle SOC, you calculate cos theta. Cos theta is adjacent side by hypotenuse. Adjacent side is R. Hypotenuse is L dash. So I can write, sorry, not L dash. Sorry. Adjacent side is L and hypotenuse is R dash. So L divided by, what is R dash? R dash is R square plus L square to the power of 1 by 2. Take this and substitute in this equation. So from figure, NOC, if I am calculating cos theta, adjacent side semilength by hypotenuse R dash, which is equal to L divided by root of R square plus L square, which can be written as L by R square plus L square to the power of 1 by 2. Take this and substitute in equation number 3. So B vector equal to minus of, you see, I'm writing like this, mu 0 divided by 4 pi into, taking this 2 and multiplying it with the QM, 2QM divided by R square plus L square into, instead of cos theta, L divided by R square plus L square to the power of 1 by 2 into I cap. Am I correct? Now on simplification, I can get like this, B vector equal to minus of mu 0 divided by 4 pi into, when I am multiplying the numerator, I can get 2QML by, when I am multiplying denominator, R square plus L square to the power of 3 by 2, because bases are same, powers can be added. So R square plus L square whole to the power of 3 by 2 into I cap. So this expression gives you the magnitude or the magnetic field at the point C along the equatorial line of the magnetic dipole or the Bohr magnet. But we can apply an approximation. What approximation? If the Bohr magnet or the magnetic dipole, if you are considering the Bohr magnet or the magnetic dipole is of shorter length, then what will happen? Is of shorter length means length L, semi-length L, or the length 2L is less than that of R. So L, the semi-length L is very, very less than that of R, or L square is very, very less than that of R square. So what is the approximation? L square can be neglected. L square can be neglected when it is compared with what? When it is compared with R square. So R square plus L square is nearly equal to R square. See, if it is R square plus L square whole to the power of 3 by 2 means, I can say that R square to the power of 3 by 2, 2 will get cancelled. So that value will be nearly equal to R cube. Therefore, what is the value of B vector? You can simplify this equation as minus of mu 0 divided by 4 pi into this 2QM into L can be written as magnetic dipole moment PM divided by this R square plus L square to the power of 3 by 2. After applying the approximation, it is R cube into I cap. Or I can write this as B vector equal to mu 0 divided by 4 pi into PM divided by R cube into minus I cap. Or we can write PM B vector equal to mu 0 divided by 4 pi into PM vector divided by R cube. Since PM into I cap is equal to PM vector. A minus, so I have to put a minus here. So this gives you the magnitude. This alone is giving you magnitude. Or we can write like this. What is the magnitude of the magnetic field? So therefore, what is the conclusion? I can write like this: magnitude of magnetic field at a point on the equatorial line, at a point on the equatorial line of magnetic dipolus, equatorial line of the magnetic dipolus, B equal to mu0 divided by 4 pi into PM vector divided by R cube, and direction is given as it is acting, that is B is acting opposite direction to that of dipole moment, See, because we are getting the answer as minus of PM vector. Minus of PM vector means it is acting in a direction opposite to dipole moment. Dipole moment is acting from south to north. Now it is opposite to dipole moment is the magnetic field acting at a point along the equatorial line is acting from north pole to south pole. This is called to be the magnetic field acting along the equatorial line. Hope you should have understood this. Now we have to compare. See, already we have studied about the magnetic field at a point along the axial line. If you are considering the magnitude of magnetic field acting along the axial line, it is given by the formula mu0 divided by 4 pi into 2 pm divided by r cube. Here now we have calculated magnetic field along the equatorial line. Magnitude of magnetic field at a point along the equatorial line is given as mu0 divided by 4 pi into pm divided by r cube. So when you are considering the ratio between the magnetic field at a point along the axial line to that of the equatorial line, then the ratio will be equal to 2/1, or it is equal to 2:1. Therefore, I can write the magnetic field at a point along the axial line is equal to 2 times the magnetic field at the point along the equatorial line. So this is the conclusion that we have right from the calculation. Hope you should have understood this concept. Further, see, we are going to study about the example number 3.6 available in the page number 138. Come on, go through the problem again. A short bar magnet has a magnetic moment of 0.5 joule per Tesla. So as we know, the magnetic moment is represented by PM, which is equal to 0.5 joule per Tesla or ampere meter square. Calculate the magnitude and direction of the magnetic field. So magnitude and the direction of magnetic field means I have to calculate B vector. Okay. Produced by a bar magnet which is kept at a distance of, so R is equal to 0.1 meter from the center of the bar magnet. The magnetic field they have asked you to calculate it along the axial line and also along the equatorial line. See, direction we can say, if it is along the axial line means it is acting in the same direction as that of the dipole moment or the positive x-axis I cap. Along the equatorial line means it is acting opposite to that of the dipole moment. That is along the negative x-axis, that is minus I cap. We know the formula. What is the magnetic field along the axial line? Magnetic field along the axial line. Magnitude is given by the formula mu0 divided by 4 pi into 2 pm divided by r cube. If you want to get the direction B vector, then you have to put it out as I cap. Now you substitute what is mu0. It is 4 pi into 10 to the power of minus 7. This divided by 4 pi into 2 into pm. Pole strength is 0.5 divided by r cube. R is 0.1. That is 10 power minus 1 the whole cube. And direction is I cap along the positive x-axis. If I am simplifying this 4 pi will get cancelled. 0.5 is nothing but 1/2. This 2 and this 2 will get cancelled. So I can get 10 power minus 7 divided by 10 power minus 1, the whole cube is 10 power minus 3. When I am dividing, I will be able to get it out as 10 power minus 4 I cap and B vector in terms of the unit Tesla. So if you want to write the magnitude B vector is equal to 10 power minus 4 Tesla. Direction is along the axial line, in the direction of dipole moment, PM, or along I cap na positive x-axis. Similarly, you move on to the equatorial line. Magnetic field at a point along the equatorial line, if it is B vector, then mu 0 divided by 4 pi into PM by R cube, but the direction is minus of I cap. So magnitude of this value, that is 0.1 by 2 into 10 power minus 4, 0.5 into 10 power minus 4 I cap minus I cap, or you have to simplify again. See, B equatorial is equal to, see this value when I am simplifying, I will be able to get 10 power minus 7 PM. It is taken to be, what is the value of PM? It is 0.5 divided by R cube is 10 power minus 3. On simplifying, you will be getting 0.5 into 10 to the power of minus 4 Tesla available in minus of I cap. So direction opposite to dipole, opposite to direction of dipole moment. Opposite to direction of dipole moment. That is minus of I cap. This is the answer. Hope you should have understood. So now we are going to obtain an expression. For the torque acting on, expression for a torque acting on a bar magnet, in a kept in a uniform magnetic field, Let us consider that uniform magnetic field as B vector and the torque available as tau vector. So how to proceed? Let us consider a diagram. So I am taking an uniform magnetic field. As you know, a uniform magnetic field is represented by drawing parallel lines. So let us consider this as the uniform magnetic field. Inside this uniform magnetic field, let us place a bar magnet. So if I am placing a bar magnet, the bar magnet is having two poles. At one end, you are having the south pole, at the other end, you are having the north pole. The distance between the two poles or length of the magnet is taken to be 2L. Now, when the pole strength available at the two ends, the pole strength of south pole is Qm. The pole strength of north pole is also Qm. When you are placing a pole strength inside an uniform magnetic field B, this pole strength at the north pole and the pole strength at the south pole are experiencing force. The force acting on the pole strength is Qm into B, acting in the same direction as that of the external magnetic field. Similarly, the force acting on the south pole by the pole strength Qm is Qm into B, but acting in a direction opposite to that of the magnetic field B. Now you see, this QMB and this QMB are equal in magnitude. QMB and QMB. What are they? These are the two forces. These are the two forces acting at the south pole and the north pole respectively. See, both are equal in magnitude. Both are equal in magnitude, but they are acting in what direction? But they are acting in opposite direction. So net translational motion is 0. Net translational motion is equal to 0. What is that net translational motion? That is along the straight line, there is no movement. So the translational movement or translatory motion is equal to 0. But what happens? But these two forces which are equal in magnitude and opposite in direction, not acting at a point, they constitute what? They constitute a couple. So they constitute a couple means what is the resultant of the couple? So the resultant of couple is rotation, or it can able to produce torque. The torque produced on this magnetic dipole is considered to be tau vector, which will try to rotate the magnet, or the magnetic dipole parallel to magnetic field, which will try to rotate the magnet or the magnetic dipole parallel to what? Parallel to the magnetic field B vector. We have to calculate that torque with tau vector. Hope you should have understood. So before going to the derivation, we have to write a small description. What is that small description? First of all, you consider a bar magnet. Consider a bar magnet of length 2L having pole strength QM, and dipole moment PM. என்ன பண்ணிருக்கிறோம்? Placed in a uniform magnetic field, making an angle theta, with magnetic lines of force, with the magnetic lines. எல்லாம் ஒரே ஸ்டெப்ல கொண்டு வந்துட்டேன். So if this is the axial line அப்படின்னா, the angle between the magnetic line and the axial line of the bar magnet, let us consider it as theta. Let O be what? Let O be the geometric center. Now, when the magnet is placed inside the uniform magnetic field, the pole strengths are experiencing a force. The force experienced by the pole strength is QM and QMB, which are equal in magnitude and opposite in direction. So since they are equal in magnitude and opposite direction, there is no net translational motion. That is, the magnetic dipole or the bar magnet won't move along a straight line. But the two forces, equal in magnitude, opposite in direction, said to constitute a couple, try to rotate the magnet. Since it tries to rotate the magnet, a torque is said to be produced. That a torque will try to align the magnet parallel to that of what? Parallel to that of the magnetic field. So we have to calculate the torque. What is that torque? So if I want to calculate the torque, before that I am writing force experienced on North Pole. What is the force experienced on North Pole? Let us write it out as F1 vector. So North Pole or South Pole or magnitude அப்படின்றது QM into B. In the direction, in the same direction as that of the magnetic field, it is along the horizontal direction, I cap எடுத்துக்கலாம். Similarly, I can write force experienced on the South Pole. What is the force experienced on the South Pole? Fs vector, which is again QM into B. It is acting in the direction opposite to that of the magnetic field. Opposite to that of the magnetic field is minus x-axis. So minus of I cap. Now, what is the moment of force or the torque? Because these two forces equal in magnitude, opposite in direction, constitute a couple, and the resultant of the couple is torque, or this resultant of the couple, we can say it out as moment of force. So I am calculating moment of force about the point O, about the center the rotate agum. So I am calculating the moment of force or moment of couple about what? About this geometric center O is equal to the torque developed about O, which is equal to டார்க்னா ரெண்டு மாதிரி பண்ணலாம். ஒன் ஆஃப் த ஃபோர்ஸ் இன்டு பெர்பெண்டிகுலர் டிஸ்டன்ஸ் அப்படின்னு எடுக்கலாம். பெர்பெண்டிகுலர் டிஸ்டன்ஸ்னா டிஸ்டன்ஸ் பிட்வீன் திஸ் QMB and this QMB in between the two lines of action. ஸோ அதை டைரக்டா போடுறதா இருந்தா 2L sin theta ன்னு போட்டுக்கலாம். பட் உங்க புக்ல அப்படி போடல. அபவுட் O கால்குலேட் பண்ணியிருக்கிறாங்க. அபவுட் Oனா from here you drop a perpendicular, from here you drop a horizontal. So what is this distance and what is this distance you have to calculate. So torque is equal to pole strength. Pole strength is considered to be QM into perpendicular distance between O and S. O and this force, that we can write it out as OS vector, plus I can write other side QM into one of the force at this end, QM into the distance is perpendicular distance from N along this direction. That is N means QMN, QMB, and this horizontal line, which is ON vector. So what is the perpendicular distance for OS vector means this length. What is the perpendicular distance for ON means this length. What is this length? See here O, here N, here O, here N. This is the horizontal line along which the force is acting. This angle is theta. So what is the component of this ON which is perpendicular to that of this angle, which is the opposite side? Let us take this point. In the distance, so you calculate sin theta. This x nu vechukren, illa y nu vechukren. Sin theta na opposite side by hypotenuse. Opposite side vandu y. Hypotenuse ngiradhu L. Y is equal to what is its value? L sin theta ngiradhu value. So OS vector, torque tau vector is equal to QM into OS is nothing but L sin theta, plus again QM into what is ON. Similarly, we can able to calculate OS as well as ON, which is also equal to L sin theta. So the total distance between the two forces is the perpendicular distance between the two force, which is equal to 2L sin theta. So on simplifying this, you can write tau vector equal to, see, QM L sin theta plus QM L sin theta. You can write 2QM L sin theta. This is magnitude of the torque. So magnitude of the torque tau is equal to, what is this 2QM? I have left out B also, isn't it? BQM, BQM, one of the force into perpendicular distance. So I have to write B also here. So BQM into L sin theta, BQM into L sin theta. So here also you will be getting 2QM LB sin theta. So I can write B into what, or 2QML. What is 2QML? 2QML is nothing but what? Nothing but dipole moment, magnetic dipole moment PM. Here it is B into sin theta. So this is considered to be magnitude of the torque acting on the magnetic dipole placed inside the uniform magnetic field. If you want to write it in vector notation, see, in vector notation, what is its value? If it is tau vector, then I can write this. See, we know A vector cross B vector can be written as AB sin theta. Like that, you are having PM B sin theta. PM is a vector quantity, B is a vector quantity. So tau vector can be written as PM vector cross B vector. If you are taking the cross product for this, you can able to get the answer as PMB sin theta. Am I correct? So this we are calling it out as, or this we are considering it as the expression for the torque acting on the magnetic dipole or bar magnet when it is placed inside a uniform magnetic field. Hope you should have understood this.